In this video, we are going to talk about contour integrals with branch cuts. So our last video, we talked about contour integrals, but if you have a multi-valued function like logs, then that's going to give you problems at integrals because you can't have multi-values. So what we do is we select branch cuts. If you recall, in one of the chapter 3 videos was about logarithms and branch cuts. So if you don't remember or haven't taken a look at that video, now might be a good time. The things I do have for your review or for your reference is the contour integrals. This is the formula if you want to integrate a function f of z over a contour c. And the steps are to parameterize the curve z of t, noting the interval for t, that the interval is going to give you your limits of integration. Then you compute f composed of z and also z prime of t. Then once you have these elements, you plug them into this formula here, which will give you the contour integral. I also have for your reference from chapter 3 the definition of log of a complex number, which is equal to natural log of r plus I theta. And obviously you put z into exponential form to get r and theta. And also the definition of an exponent of a complex number, which is equal to e to the c log of z. In this video, we are going to look at branch cuts. In particular, we are going to look at these path or contour integrals that contain a branch cut of the function of the integrand involved. And to see how we treat these contour integrals that contain a branch cut, we're going to use this example to motivate our discussion. For this problem, we want to integrate a function f of z, which I will show you in a minute, around this path c. It is a semicircular path, only the top half of a circle, and you can see the radius is 3, so we have z equals 3 e to the I theta, and what gives us the top half is parameterizing that theta will go from 0 to pi. So it doesn't have the pi to 2 pi, so it cuts out the bottom half. And we specifically, because theta can equal 0 and it can equal pi, we are including the point z equals 3 to z equals negative 3. So actually writing this is sort of redundant because I've already told you that theta will go from 0 and pi, including the endpoints. The function we want to integrate, our f of z, is equal to z to the 1/2. And using our definition of a complex number raised to an exponent, that's equal to e to the 1/2 log of z. And we can see this is a multi-valued function. For example, if you plug in 9, you can see we get two values, plus and minus 3. We can make our function f of z single-valued by limiting what values we have for our z. In particular, we can say z is greater than 0, and that will still give us a possibility of a multi-valued function. But the other thing, z, when we write it in exponential form, we can insist that the arg of z, or the angle of z, stays between 0 and 2 pi, not including 0, not including 2 pi, because if you include them, then 0 and 2 pi is a possibility for a multi-valued function. So essentially we get rid of this line here. So that is our branch cut line at 0, which is equal to 2 pi. So what we're saying is when we choose our values for z, and remember z is of the form e to the I theta with a radius. So it's this periodic form. And when you come back to 2 pi, when you cross the branch cut, you get a whole nother set of values. But what we're saying is we're only going to consider values from 0 to 2 pi, and we're not going to include this line. We never cross this line, so we make our value single function. I'm sorry, I meant to say we make our function single valued. What this has done for us, though, is now over here for the value z equals 3, we no longer have it defined because our function is only defined up to values less than pi over 2 or greater than 0. It is not defined here. So our function is no longer defined at 3. So this seems like it might cause a problem because 3 is the start of our contour C, right? We wanted C to go from including 0 to pi. We wanted to include this point 3. However, that isn't going to be a problem because our integrand, our f of z, is piecewise continuous. In other words, the limit at this point exists. So we don't actually have to have the point for our integral. We don't have to have the point 3 defined. Just the limit at the point 3 has to exist. So in other words, the integral on our contour, including the endpoints 3 and negative 3, exists because the integrand, that's the integrand as our function, is piecewise continuous on C, so it's still continuous. And to show the continuity, we will show that the limit exists at what we're trying to integrate. I cleared out some of the extra notes and I moved things up so I can show that the integrand is continuous by showing that the endpoint, I'm going to focus on the endpoint where we have doubts, z equals 3 has a limit. In other words, the limit exists, it is continuous at that point. So to show that this integral and this integrand is continuous so we can perform this integral, first we're going to identify our path, our curve, z of t, and actually because it's we're parameterizing with theta, I should have put z of theta is equal to 3e to the I theta, and our f of z that we're integrating is over here. Z equals 1/2, f of z is equal to z to the 1/2, and using our definition of complex exponents, that's equal to e to the 1/2 log of z. The next thing to do then is to compute f composed of z and z prime of t. So f composed of z, so I need to find our z, that's 3e to the I theta, and we're going to plug that into f of z. So we have e to the 1/2 log of 3 to the I theta. So this is what I've written here. E to the 1/2 log 3e to the I theta. Now I'm going to use the definition of my logarithm of a complex number so that my 3e to the, or log 3e to the I theta becomes natural log of 3 plus I theta. Using properties of exponents, I simplify this down to square root of 3e to the I theta over 2. Next, I need to compute z prime of t. Again, this should be a theta, just wherever I have t, remember that in this particular example, we're parameterizing using theta. So the I just comes down as a constant, so we have 3i e to the I theta. For my integrand, now I'm going to multiply f composed of z times z prime of t. And I've done this here. I have my f composed of z and my z prime of theta. And then you can see my algebra. I algebraically simplified this to 3 square root of 3i e to the I 3 theta over 2. And then I used Euler's identity. And then I kind of multiplied the I in to get this last expression, which is 3 square root of 3 minus sine 3 theta over 2 plus I cosine 3 theta over 2. And remember, our goal is to show that the integrand is continuous, that our integrand here can be integrated, in particular at the point z equals 3, because z equals 3 is not defined at that function. So what we're going to do is look and see that the limits of our integrand exist and what the limit is. So the limit as theta approaches 0 from the positive side. So we're only worried about the limit as theta approaches 0 from the positive side because our curve and our integration is only occurring above the x-axis, right? We're not doing anything over here where we're approaching 0 from the negative side. So we're only worried about approaching from the positive side. 3 square root of 3 sine 3 theta over 2. When we plug this in, sine is 0, 0, so we get 0. And the limit as theta approaches 0 from the positive side of our I cosine 3 theta over 2, and I should put in my I, which I squeezed in, is equal to, this is just at 0, this is 1, so we have 3 square root of 3i, so the limit exists. And in particular, at our point, z equals 3, the limit is I 3 square root of 3, or where z equals 3 and theta is equal to 0. Our limit is I 3 square root of 3. So the limit exists. Our function is continuous on the interval theta equals 0 to pi, including the endpoints, when we define its value at theta equals 0 as I 3 square root of 3. In other words, we define it as where the limit says it's approaching, and therefore it will be continuous. And since it's continuous, we can therefore take the integral. Now that we've justified being able to take the integral because the integrand is continuous, I am actually going to take the integral. So I cleared out all the words that justified why we can take the integral, and now I can work on taking the integral, and I saved this because I need this to take the integral. I need my f composed of z prime of t. So my integral of along the path c of z to the 1/2 dz is equal to, now here I took this portion. I didn't use Euler's identity, but I have the 3 square root of 3i, and then my integral is going to go from 0 to pi, e to the I 3 theta over 2 d theta. So remember, I can then take the integral of this, and I get 2 over 3i e to the I 3 theta over 2 evaluated at pi and at 0. I plug in algebraically, and I get negative 2 square root of 3 minus 2 square root of 3i. That was kind of a long example, but you just want to remember that this whole portion here is just proving that the function is continuous, and we can go ahead and do the integral. Here's the actual integral, well, plus you needed this line as well. We will move along now to another example. The example is, suppose C is the positively oriented circle z equals r e to the I theta, theta between negative pi and pi, about the origin. Let A be a real number. Using the principal branch of f of z equals z to the a minus 1, which using our definition of a complex number to an exponent is equal to e to the a minus 1 log of z, and our principal branch is going to tell us that the modulus of z is greater than 0, and the argument of z, in other words, the theta associated with the z, is going to be between negative pi and pi. Remember, this is the restriction that makes it the principal branch. So we want to evaluate the integral over c. Where is our c? C is that circle of z of a minus 1 dz. So this is our function that we're integrating. The first step is to parameterize our curve, z of t, noting the interval. And that has already been done for us. So it's z equals r e to the I theta, theta going between negative pi and pi. So the first step is done for us. Now we need to compute f composed of z and z prime of t. So f composed of z of theta, so we plug in our r e to the I theta into our f of z. So that'll give us e to the a minus 1 log of r e to the I theta. So that's what I've written here. So we're f of, we plug in our z, which is r e to the I theta, e to the a minus 1 log of r e to the I theta. Algebraically, I've done some algebraic manipulations until I get to r raised to the a minus 1 and e raised to the a minus 1 I theta. Z prime of theta, where is z? It's over here. We just bring down the constant I, and we get I r e to the I theta. And then I'm going to multiply my f composed of z, z prime of theta, because that's what I'm going to put into my integral. So I have my f composed of z times z prime of theta, and I simplified it to I r to the a e to the I theta over a. And I went ahead and used the Euler's identity on here, but then I didn't use it. So you can ignore this if you'd like, or you can take a look. So finally, my integral, I'm going to pull this out because these are just constants. I r to the a, integrating from negative pi to pi, e to the I a theta d theta, and you can see the rest is integration and simplification. using the relation to get a sign. But this is my final answer. As you can see, if you don't have to look at this and see what the limits approach and make sure that it converges and you can take the integral, this process goes fairly quickly. To review what we've gone through, we looked at the formula for the contour integral. We looked at the formula that defines the logarithm of a complex number z and the formula that defines the exponent of a complex number z. And then we looked at contour integrals that contain a point on the branch cut, so that will not be defined of the integrand. The integrand is just what we're integrating. And we did this example here in painful detail, also justifying why our integral was defined at the branch cut, not defined, why it's continuous, and then we can take the integral, and the integral was over here. For review, I have this one problem here for you to try. I suggest you pause the video, give the problem a try, and when you come back, I will have a solution for you. Here is the solution, and that is it for this video. Thank you for watching.